All right, so here we are going to learn how to apply our skill in taking definite integral into finding average value of a function. So this video lecture here is one among the many applications of definite integral, of finding a definite integral. Okay, so to get started with the idea, let me bring up a couple basics right here. Let me bring up a couple basic understanding. So I'm going to need to swing over to the other board right there. Okay, so finding average value in these days is something that's done very commonly throughout, throughout a lot of different careers right there. Okay, and surprisingly, they are starting to teach like even second grade kids about how to do average value. So what exactly, how do we find average value? How do we find average value? When I'm asking this question to anyone, either a stats student or a formal math major student or any any person, the answer I'm going to hear is we're going to add up all the values and divide it by the number of values they are, divided by the number of, how many values there are. That is correct. That is true. And we don't have to wait until like a formal college math to know that truth. Like I said earlier, they're starting to teach even second grade students about how to do this. Maybe I'm a little over exaggerating, but at a very young age, at elementary level, elementary school, they're starting to teach the children these, as long as the children starting to know how to divide. Okay, and so now think about it. If we have a list of y value, for example, y1, y2, and y3, it's a list. Okay, we have a list of value, a whole bunch of values. That's the idea right there. And then up to the last value right there. And so just like that question I brought up earlier, how do we find the average of these? So if we have a list, and of course maybe we have some values, some value here is equal to the other values, but in the end we have n physical data points, value points on our list right here. Or another way of saying we have n members of this list. Okay, so finding the average value of this list right here, it has a lot of applications for a teacher. A lot of times students ask me, hey, Mr. Dung, hey, the professor, what is the average exam score? Okay, so what I do here, I'm going through the entire list of exam scores in front of me, and so now what do we do to find the average? y1 value plus y2 value plus y3 value, keep adding, etc. and etc. up to the end of the list, yn, and then we're going to divide by n. And that's exactly the mathematical interpretation of how people have been verbalizing it. We're going to add up all the values and divide by how many numbers there are. How many numbers there are. Okay, so that's just what it is. So this is called the average value, y bar. That's one of the common symbol, or y average. Okay, like an y with a subscript avg is another symbol for the average value of all these on this list of all the y values. Okay, and so now with that brief basic understanding, average value of a function. Now let me bring up a function on the computer screen here. Okay, you don't have to worry about what function this is, but just any function has a graph, and at any x value. So here's my graphing space right here. Let me put up a function. Okay, some arbitrary function. And so now a function can have a height at anywhere. So think about we have a height here. Okay, think about we have a height anywhere else at many different heights right here. So we can have a height here, we can have a height there. Don't worry about the shading yet, okay? But we can have so many heights. And so now let's say for a function, just like that, for any function, then the average value of a function, we have to, before we can do that, we have to, more precisely, we have to restrict our functions within an interval. Okay, so a function, I'm just trying to recreate that picture that you have seen on the computer screen earlier. But so now, suppose we have a function. So value of a function is going to be the height anywhere at, the height of the function, because it's the output. So it's the height of the function at any value x. And so now in our scenario here where we are where we are restricting our function inside an interval from a to b right here, then let's say you have a value here, x1, okay, and then x2 and x3, okay, and so just between these three and including a and b right here, so maybe I can call this x0 for a, and then this is x4 for that, right? We got 1, 2, 3, 4, 5 values, okay, because we have 5 different heights, up and down, up and down. And so for a discrete setting like this, so I'm using that term discrete, means we got a finite number, countable number of x values, and consequently those produce function output values. And so in that case, the average value on this set of function outputs, so this height right here is f of a, or f at x of 0. Okay, that set right here, I mean that particular height right here, visually displayed on the graph, there is the function output at x1. And then this function height right here, and none of the height is exactly the same, but maybe some height is equal to another height, but they are different heights at different x values, okay? And so the function output at x2, okay, is another height, and then we got f of x3, we have f of x4, okay, and we have okay, so we have all those 4, so maybe let me write it in a little bit closer. So f of x0, f of x1, okay, f of x2, okay, and then we have f of x3, and the last one here on the list, f of x4, okay. So now those are the ones, those are the heights, right, that at different x inputs. But now the average value, at least for these discrete ones right here, we're going to need to simply add. Okay, and how many values are there? How many function output values are there? There are 5 of those, so we're dividing by 5. Okay, and so I used my index a little bit out of ordinary, but I should have gone with x1, x2, x3, x4, x5 to make it more consistent with the fact that we have 5 values, but that should be okay. But now the idea is, see, just like how we have been finding, and just like how it has been popularly known, okay, average value, it has to be done by adding up all the values, right, and divide by how many there are. So in that way, so this is the brief basic when we apply that concept into a function. At different average value of a function, we just simply add up, right? We add up the different heights, different function output values, and then divide by how many there are. Okay? But now, I said earlier, this is the case where we have discrete x values. We're looking at a discrete countable number of x values inside this interval over here. But now the problem becomes more challenging, and especially for us, the people who are studying the integral calculus. Normally throughout many the colleges, they refer to this as a calculus 2 level right here. Then what's the idea here? We're not going to look at only a limited, discrete, finite number of outputs, but we're looking at an infinite, because now let me erase this picture. Okay, but keep in mind now, since I already erased the quick little work right here, keep in mind that we're adding all the heights and divide. We're adding all the heights and divide by how many, we're adding all the vertical height, which represents the outputs of the function. So we have to add up all the outputs of the function and divide by how many there are. Okay, but now in our situation here currently, and we have already learned about the definite integral that works on the idea of accumulation. So first of all, now we're gonna inside of this interval from a to b, we're not only having a finite, we're not only having a few heights. I mean, between a and that x1, I called that earlier, then there are infinitely many stripes in between already. Okay, there are a lot of stripes. And so now in that case, let me even completely erase all the stripes I've made so far in this picture. And now you're gonna have to start imagining. Only between a and b, only from a to b, just in that interval, no matter how short or how long the interval is, there are going to be infinitely many number of stripes right there. simply due to the reason that there are infinitely many x values that we can fit in between a and b, anywhere from a to b like that. Okay, and so in that way, we still going to add up the stripe, but that works right there. See, the first stripe, I mean the first x value, the first output value is this first stripe, and then there's the next stripe, and then the next stripe, over and over, and so adding up and accumulating. That's why we are doing the integral over here, a definite integral accumulating from a to b, okay, of all the function values at different x value. So that's definite integral over here is accumulation. We're adding up, okay, we're adding up all of the stripes right there from the beginning to the end. It's accumulation. And so I should have also mentioned, so right at the beginning point right here, I should have also mentioned, so up to this point in your learning, a definite integral is accumulation. And that's why this finding average value is a perfect place to apply your understanding of accumulation, of doing a definite integral. So we're accumulating all the stripes, right, from the beginning point to the ending point right here, from that starting a value to the ending b value. But now that's only so this summing up right here, this accumulation is only equivalent. It's only, you gotta take my word for that. This is only equivalent to the adding up, because remember, finding an average value, you have to first add up all the values. That's what this accumulation is for. But now where's the division part? We need to divide. After adding, we need to divide by how many values there are. Okay? So now in that situation where we have infinitely many stripes, then we're gonna divide. But here's the way how we divide. We're gonna multiply this accumulation by 1 over the total length, just the total length from a to b, which is 1 over b minus a in the denominator. That is how we're gonna obtain our. That is how we are going to obtain our average function, average output function, or average value of a function right here, okay, for the function f. And so many textbooks use f with a subscript avg, and also there are textbooks who also use f with a bar on top to make it more like a statistic setting right here. So the f bar is also another version of saying this is the average, the average value of the function f. The bar is the average, so average value of the function f. Okay, and so my way of explaining it is just to make things a little bit close to the statistical understanding, to those who having some background or have done a little bit of statistics, even very elementary statistics. But my way of explanation, my way of explaining this work right here is not a formal proof of how people came up, or how mathematicians came up with this formula. Okay, so but the actual reasoning is given throughout all over the standard calculus textbooks out there. Just grab any standard calculus textbook and you should see a much more formal the reasoning that lead to that formula. Okay, but so now, as I have just said it, this is now the formula that we can use to find average value. And so now, so in that way, and now I can just erase the title of our discussion topic here. So any standard calculus textbook is gonna call this formula I just erased here, and I'm about to rewrite that here. But the textbook regard to that formula as a definition. But now the way I see that, it's a definition, but there are good reasoning leading to it. Okay, it's a definition, but having good reasoning leading to defining things that way. Okay, so it's not just like a definition as like, hey, we define that thing to be called like that. Okay, so here, so I'm gonna stay with the way how many textbooks define it. So let f of x be a function. Okay, define and continuous at least. See, so we need the function to be defined and to be continuous on at least some interval from a to b. Okay, so and after that preliminary, then we have then the average. Okay, the average value of f of x. okay, on the interval or over the interval from a to b, okay, is and this is the wording that I've seen in many textbooks, so I'll stay with that, is defined by, so just now as I said earlier, many textbooks could regard to this formula as a definition, okay, but I see that it's a definition with the reasoning that leads to it, okay, so the average value of the function f of x over that interval is defined by the formula, so I use, I'm more comfortable with f with the bar on top, so f bar, average value of f, equals 1 over b minus a, okay, it's the length of the 1 over the length of the interval multiplied with the integral, the definite integral from a to b of the function f of x dx, okay, and then so now note that, okay, so also make a note that we can also use, anyone can also use f with a subscript avg like that, that's to indicate the average value of this function f of x. Okay, but this is the formula mainly focused at in this particular lecture right here. Okay, so there we go. We found a way. Okay, we found a way to find average value. All right, so what's the meaning of an average value? Why does average value bother for us? I mean, why do we bother knowing about average value? At least geometrically, I can explain right now in front of the camera in this video lecture here is we have a function, right? And so from a to b, so now as you have seen through many times, all function output values inside of this interval happen at different heights, up and down, see, up, down, and up and down like that. So average height, average function value, average value of a function means throughout all of these up and down heights right here, about which height is that this height right here is the average. It doesn't look like that, but about is this height right there is about the average. So there has to be a line right here. There has to be a height. There has to be a height where, you know, averaging out all of these heights up and down vertical heights, we're going to reach to this, what's so-called the average height. That's what it is. Okay, that's the meaning with that. Okay, and then of course, because there are applications out there where people need to find average value. And so that's why, we studied that here, but then, as a specific application of why we need to find the average value of a function, I will leave that for your specialized class, after you graduate from this Calculus 2 course right here and ready to make your way into a more advanced course, and you will see how it will be applied out there. Okay, so here I just, stay with stay very focused on just, what it is, okay, and then we're gonna design example. We're gonna look at examples that are directly, right from how we define the average value. That's all. But so now that's what it is. The average height here. See all the heights up and down. I'm looking for, we want to calculate the average height, the heights where averaging out all of these stripes right here, striped height, and we're gonna reach to that height. Okay. All right. And so now in that way, let me now erase my board. And we can start getting into our first example. All right, so let's now call that example 1 right here. Okay, and this is, I think we only need we don't need part A, part B, and part C for this particular example. One problem here stands on its own right here. So I'm going to say let f of x, okay, be defined as x squared plus 1. Okay. And this is on the interval from -1 to 2. Okay, so we have a function. Okay, it's a continuous function. Anyone that arriving at this class should be able to decide how this function here is a continuous function, and at least it's continuous on that interval given over here. Okay, anywhere from -1 to 2. So the simplest instruction about this problem find the average, or how about let me get anyone viewing this video, comfortable with reading the symbol. So how about just for short, find f bar. Okay, find f bar. So f bar here, I gotta clarify at this point right here, f bar in the way it is. Back to the formula that I introduced right here, f bar is defined, is given as a definite integral. Okay, and then multiply with a coefficient value 1 over b minus a. Okay, so now I have to be clear. Aside from that 1 over b minus a, then this part right here is entirely a definite integral. Okay, and so I discussed earlier in one of my earlier lectures that a definite integral must always give a numerical value, not a variable expression. So this is going to give us a numerical value. And then after having a numerical value coming out from this definite integral, this expression 1 over b minus a is also another numerical value. So numerical value multiplied with a numerical value. So it needless to say at this point our final f bar right here, average value of the function, has to be a numerical value, one particular value right there. I was talking about the height, right? A specific height. So it's not going to be a variable expression. Okay. So now in that way, so finding f bar right here. So, and verbally speaking, finding the average value of our function f. So now a very straightforward and direct example. F bar can be found according to what we have seen earlier, and I just had it on the board earlier. So now our interval here is from -1 to 2. So I'm setting that up to be a 1. It's a fraction 1 over, okay, and then 2 is the ending point of the interval minus -1. Okay, ending point minus the beginning point of our interval. And then now I'm going to multiply this quotient here with the integral from -1 to 2. All right, and then now it's our function x squared plus 1. And we're integrating that. We're taking the definite integral of this function x squared plus 1 in respect to x right there, on the interval from -1 to 2 right there. And that is the complete setup for our f bar value right there, our average value of the function. Okay, so in that way we are ready for the final work right here. Well, that gives us a 1/3. So maybe I should write it here to continue my line. It's a 1/3, and to be multiplied with whatever comes out from the integral from -1 to 2 of the x squared plus 1 function. Okay, and of course it's multiplied with the dx. So now we're going to start using the fundamental theorem of calculus, the second part, to find, to evaluate this definite integral. So now I'm looking at 1/3, and to multiply with the antiderivative of the function x squared plus 1 is now going to be a 1/3 x cubed plus x. Okay, and now I'm going to evaluate all of that from -1 to 2. Like that. Okay, and so it's going to be a, in parentheses, 1/3 times, and actually let me distribute that 1/3 to each term here as well. So it's going to be a 1/9 right here, 1/9 times 2 cubed plus 1/3 times 2. That's the antiderivative at at x equals 2, and then I'm going to subtract. Okay, and then for the other part, it's going to be a 1/9 times -1 cubed plus now 1/3 times -1. Okay, and so now I'm going to quickly step away for a quick calculation of all this here, and then I'll come back with a final answer. All right, and so the final answer come out after all being 2. Okay, so the function height here, the function average height is a 2. All right, and so now after this point right here, allow me to put the graph on the computer screen to illustrate the idea right here. All right, so here we are at the graph for our function x squared plus 1, f of x equals x squared plus 1. All right, and so now let me actually show the numbers. So now in the interval from -1 to 2, this is what the interval is looking like. Okay, so now with all the stripes inside, with all the stripes representing, with all the vertical stripes, vertical heights representing the function output values inside right here, then you can see that now I can put up a handle right here. So each handle represents. So see, and don't worry about the blue shading right here. Actually, I can hide away the blue shading. Okay, but now as we are accumulating from the left to the right here, you can see that our function's height, function's value as the vertical purple height right here is changing. Okay, it started at some height and then it dropped down to a low height and then it keeps rising up again and it getting higher. So again, I want you to observe and pay close attention to the behavior of the stripe, in purple color right here, that happens anywhere between our interval from -1 to 2 here. Okay, so the point again is that we have, just from -1 to 2, the function goes through infinitely many different heights, okay, or infinitely many different function output values like that. Okay, so just now, based on our calculation, we came up with the function output value, the average value of our function, or the average height, the average output value is a 2. The average height is a 2. So that means, again on the graph here, okay, for anyone to have a picture in mind, and the height being 2 is about this much. All right, this red line right here is this horizontal line is right at y equals 2 right there. And now it's really not a graph, so allow me to put that in dotted line right there. Okay, so this dotted line right here means, you see, so at somewhere, I mean, we will definitely hit, I mean, some height here, see, right at the first point of the interval here, we had a height. We already have a height that reached that height being 2 right here, and at somewhere else in the side of this interval, and I said that somewhere else inside of this interval, we have another instance where we reach the same height being 2 right here. But so that height, y equals 2, that height 2 is considered as the average value of all the height right here. So heights go up and down all over, but the average is at 2 for this particular function. For this particular function on inside of that interval from -1 to 2. Okay, but so now in that illustration I put on Desmos.com like that, and I started saying it at some point inside of that interval. So now I'm talking about on the x-axis. Okay, now I'm talking about on the x-axis. Now some point inside, somewhere inside of this interval, either at one of the two ends, and which is what happens here. It happens at when x equals -1, we reach a height. The graph, at least the graph is showing so, and then somewhere else inside we also have another value. Okay, we have another value that stays inside. So that brings up, that motivates another idea that a lot of times there is a need to look for an x value inside. Say in this particular example, we know that, on the x-axis we're inside of that interval from -1 to 2. But so we wonder, and we have already found that, hey, inside of that interval, this function has average height as 2. But so now, continuing from what I'm saying earlier, I want to find out, hey, what about inside of that interval? Where is the x value? Where can it be? Where as the x value can it be to reach that height here, to reach that average height? Okay, to reach that average height. All right, and so now let's look at example 2 right here. Allow me to stay with the exact same function, but now I'm going to call that example 2, and we can think of example 1 and example 2 are are connected with each other. Okay, but they're serving different purpose, so I design them as 2 different examples like that. So let f of x be that same function, x squared plus 1, right? And we're working on that over the interval from -1 to 2. Okay, so now here's our purpose. We want to find the value c, okay, inside of the anywhere from -1 to 2, satisfying the function at c. So basically c here is a value on the x-axis, or in other words, it's an x value being inside of this interval, but I want that x value satisfy the function value at x equals c must equals f bar. Okay, let's have a try on that. And now at this point we should be mature enough to handle this problem. So I want to find c in the interval. Okay, so just back on the graph with that illustration I've had earlier, see, the c could be here, or the c could be somewhere there. So where precisely is that c? I mean, right now I have the axis label, so viewers might see this as, hey, maybe c is 1 and c is -1, but you know, that's just the graphical. But how can we guarantee that it lands right on x equals 1, or really is it really landing right on x equals -1? Okay, so a graph is only good for an estimation, an approximation, or a prediction, but in the end we have to do that with a solid method right there. Okay, with a solid written work. So now that's all we know. We want to find a c value being anywhere inside of this interval from -1 to 2. And then we want that c, once we found it, we want the c value to satisfy this requirement, the function's height. See, f at c, f of c, the function's height at x equals c must equal the average value. Okay, so I use the exact same function to save any one of us here an effort to find the function value here, because we already had that function value from example 1. Okay, but as a different scenario in other case, like that, in other case where you are working with a completely brand new function, I mean, it's the exact same problem, but you're working with a brand new function and on a different interval, then you must start out by finding out what your function average value is first, and then from there we're going to proceed with the work. But so now allow me to start getting into the work right here. We want f of c. We want a c inside of this interval that's equal the function that's equal to the function's average value. But what was it from the earlier problem? That is 2, because we already knew f bar equals 2, the function's average height, the function's average output value, okay, or the function's the average vertical height right there. Okay, and so we knew that from example 1. But now for any c value, for any x value equals c, for any x equals c, f at c generally means what? Hey, our function is right here, f of x equals x squared plus 1. So f of c on the left hand side means we're looking at c squared plus 1 equals 2. And we need to find c. We need to find c. So right here from this equation, all of a sudden we realize we have produced for ourselves an equation. I'm not saying it's a quadratic, I'm not saying it's a cubic equation, I'm not saying it's a linear, I'm just saying it's an equation. And we need to, from this equation, we just simply have to solve for c right there as a variable. So this equation of ours right here, since we're finding c and currently c is unknown, that means it's an equation for us to solve for c as the unknown. Okay, and then yes, recognizing that as a quadratic or as whatever that is, I leave that for viewers to understand on your own, for viewers, for students of mine to know. Okay, so in this problem here, yes, it's a quadratic. So you already learned your technique right here to solve, and you don't have to go with the technique to solve this equation based on follow with my own method. You can have your own choice of the method to solve this as well. So I subtract that 2 over to the left hand side, so to write that as a c squared minus 1. So I use factoring methods right here, turning that into a c minus 1 times c plus 1 right there. Okay, and then there I'm turning that into, and that now I conclude that my solution for this has to be c equals plus and minus 1. So what's the meaning? What's the meaning of this? Okay, what's the meaning of this? C equals plus and minus 1. That means we have found it. We found that inside of this interval there are 2 values for c. There are 2 x value. Okay, and that's why we call it C here. There are two x values, two C values on the x-axis. How's that? Okay, to make it precise, two C values on the x-axis inside of this interval that satisfy the requirement that f of C equals f bar. Okay, so now this is what's making it consistent with what we saw on the graph earlier, that when x equals -1 precisely, we had that height reaching up to that dotted line right here. This is y equals 2. So when x equals -1, the function does reach to the average value. And when x equals 1 right here, the function will once again reach to the height, or reach to the value that is equal to the average value. Okay, and that's how it happens. And so along that way, now let me introduce an important theorem. Okay, so in that example, we just found that we did an actual solving work to find out where inside of the interval, inside of a designated interval, that we can reach, because this formula here, according to our definition, this formula only shows the calculation of the mean value. And then in example 2, just now, we found out that, so after we found the average value, the average height, then where inside of that interval can we, which one is the x value inside of that interval, so that we can reach to the average value. Okay, but now let me introduce a theorem. All right, so the theorem here is regarded as the mean value theorem. Okay, but then this is the mean value theorem. I have to open parentheses here for integrals, and I will explain that later. All right, it's for integrals. Okay, so I'm going to start out with let f of x be defined and continuous. Okay, be defined and continuous on the interval from A to B. Okay, and so in that way, once we had that, then the important statements of the mean value theorem is stating as follows. Once we've had all that the prerequisites for our function, it has to be a defined and then continuous in that interval, then there must be, okay, at least, allow me to word it in my own words a little bit unlike the way how it's stated too formally in many textbooks out there. But then feel free to use your textbook to compare the wordings like that. So what I'm saying now, according to the theorem, it's stating that there must be at least a value C inside of that interval from A to B right here. Okay, there must be at least. And what's important here is at least. Okay, at least a value C inside of that interval that's satisfying. So the C here is that the value C is the one that's satisfying f of C equals the function average. So of course we learned about this theorem definitely after we have learned how to calculate f bar. Okay, but so now really what is the impact, what is the usefulness of this theorem? I have to honestly admit, at our calculus 2 level or at our integral level, we are beginning in our the integral learning right here, then we don't see much of a usefulness of this theorem yet. Okay, but the real usefulness come out when we arrive at a a more advanced course in mathematics. Okay, but right here I can point out, that this theorem right here, at least for me, back to that problem right here, back to this problem. See, I was looking for a C value. Inside of this interval to satisfy. But now think about my role here as the person who was about to do it, Then even before I wrote down any of the steps to do it, before I start spending my efforts of doing that, then the theorem already helps me determine that whether or not I should proceed. Okay, let me repeat. Having the understanding of the theorem in mind, right there, the theorem helped me decide whether or not I should proceed into this problem. Because see, the function here itself is continuous. It's defined and continuous in that interval. So the theorem already guaranteed for me that, so hey, inside of that interval, we should be successful. That's what it says. We should be successful successful in terms of finding a C value, at least one C value inside of this interval. Okay, that satisfies this requirement. Okay, that requirement f of C equals the function average value. So that's what the theorem is for. So before we lay down our efforts, before we spend our effort and lay down the steps to solve for that C, to particularly find that C, we must be acknowledged that there should be a value there to find. Otherwise, if there's no guarantee that our work will come out with a value, then why do we spend our efforts? Okay, and so this mean value theorem here is a sense about a guarantee. It guarantees for us that anytime our function is defined and continuous in that interval, okay, then there will be a value C inside of the interval. It could land right on the interval limits as well. Okay, but there will be at least one value that satisfies us. And so once we knew that there will be a value, then we're gonna go ahead and make our attempt to solve. And so that's why, back in my example 2 earlier, I spent my effort solving because I knew in the back of my mind, and with the understanding of that theorem, that there will be a solution, there will be an existing value. That's why it's worth it to find, and that's how I decided to go on and write that here as an example. Okay, but then as a real usefulness, as a solid usefulness of this mean value theorem right here, then we have to wait for a more advanced course in mathematics, sort of like a math major junior or senior course right there, in order to see the actual mean value theorem applied right there. All right, but so now the reason I have to open the parentheses here and say the mean value theorem but open parentheses for integrals, because now sadly the term mean value theorem is a little bit overused throughout the 2 courses, the calculus 1, which primarily studied about differential calculus, and the calculus 2 here, which primarily studies about integral calculus. So if you recall, of course, as you arrive at this video lesson, then you must have gone through a course in Calc 1 or a course in differential calculus. Back then in your days, learning how to find derivatives, there was also a mean value theorem. You can always search back even throughout my video lectures, or you can search back with your own instructor where you were taking your differential calculus. But there was a mean value theorem, exactly the same name, the mean value theorem, back then in your days doing differential calculus. And that in those days the theorem itself was simply named the mean value theorem. And so now when we arrive at this level, being in a Calc 2 course, an integral calculus course, if I simply use that name, mean value theorem, again, many students will fall into that misunderstanding and will get trapped into a serious misunderstanding. So here specifically, it's called, sadly, it's the same name, it's a mean value theorem, but I have to always open parentheses when I'm with students. It's a mean value theorem, the kind of mean value theorem that for integrals, okay? Because we use the integrals to come up with average. All right, and so now the last piece of information, needless to say, why is it called mean value theorem? See, because just now I talked about in the entire lecture here, it's all about the average value. And so mean value is a formal name for the average value. Okay, and that's the reason why this theorem here is called the mean value theorem, and allow me to, you know, to do a couple, I mean, a double or triple underline on that word mean value theorem. Okay.